So today we are going to finally get into plasticity. So far we have spent lectures really 3 through 8 only focused on the elastic regime. Basically, lectures 3 through 8, stage 1, where we can have equations relate stress and strain. We're going to spend lecture 9 on plasticity, stage 2, and then lecture 10 on stage 3. Plasticity, plastic deformation, permanent, irreversible. So we don't have relationships constitutive, first principles relationship that relate stress and strain to one another. Instead, we're going to have to rely on evidence-based empirical equations. We're also going to talk about what happens to your plastic deformation mechanisms when temperatures increase, specifically creep at higher temperatures, and see how that affects materials. You can measure plasticity, and specifically yield strength is going to be one of the critical criteria that we're talking about. You can measure it in several different ways, but before we get too deep into this, let's take a step back and think about, theoretically, what should be the yield strength of materials. And we could actually derive this with a relatively simple first principle equation, as we're going to see looking at a perfect crystal. And if I were to yield something, I would shear this lattice, and they should basically slide one atomic length, or one atom, basically that distance A past one another. So I can look at the force required to do this. So if I look at some maximum force, if I look at, treat this like a sine wave, at x equals 0, where the atom's at its original position, my stress should be 0. Makes sense. If I'm at 2 pi a over a, which is 1 sine of 2 pi, will also be 0 because I'm in my equilibrium, my correct distance effectively. My shear stresses should be maximized when I'm at a distance x equals a over 2. So at sine of pi, I know that's going to be equal to 1. So there, my shear stress will be the maximum shear stress. So we can cancel that out, pi, and then we're basically good to go here. So I could look at the engineering shear strain as that results. I could do a little bit of basically a chain rule as well, and I could find, if I evaluate it at where that shear should be equal to 0 or as it approaches 0, and I could develop an expression for my shear modulus, and I can relate that tau max, my maximum shear stress that the material should undergo, and you see it's this g over 2 pi, basically about g over 10. Now, that should be about 10 gigapascals for most materials. But we know experimentally the yield stress is around 10 to 100 megapascals. That's 3 orders of magnitude off. Why is this happening? What's going on? It's a question that was profound and stumped people for many, 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 many years. But the answer to that lies in everything in this class is defects and dislocation theory. And we're going to get into dislocation here. We assumed a perfect crystal. Defects explain why materials yield at stresses much, much lower than what is perfectly or theoretically predicted. Taylor, Polanyi, Orwan, they all envisioned this well before it was proved atomistically. So it's easier to break one bond at a time than entire, essentially, planes of atoms. So we've hinted before about these local stress and strain fields around the dislocations, at the top and bottom of atoms, compression, tensile regions. There's different interplanar distances between FCC close packed planes and BCC non-close packed planes that will essentially change, the distortion in your lattice. So all of these things are coming back now in what we're seeing here. And they are going to affect yield stress phenomena. They're going to affect dislocation motion. These regions of compression at the top of our dislocation and tension at the bottom, they are going to change the way that atoms diffuse or move, or how dislocations interact with each other, how dislocations interact with point defects. And we're going to see it's going to be difficult to move, through this, through these lattices. But again, because you have this extra half plane, it's easier to move than breaking, the entire plane of atoms. So that's kind of the key distinction here, and we're going to see this difference in distortion. And eventually, it's going to depend on a lot of factors, slip, the motion of those dislocations. We're going to eventually also calculate and actually one of the things that you can see here that's kind of wrong, you would assume that this would be a metastable position. It's a great observation, but it is completely wrong. And the fact is, when you're moving essentially this edge dislocation, you have to drag these compressive and tensile regimes around. So we're going to actually calculate a Pierre's force, a PK force on the dislocation. So there's going to be when a stress is applied to the system, there's going to be stress on the dislocation. Dislocations have their own stress field that will affect other dislocations. And we'll see that the force will typically be smaller for FCC than BCC because of that difference in interplanar distances and the distortion on our lattice. So based on all the things we talked about in lectures 1 and lectures 2 in structure, that is going to have a huge impact on where these edge dislocations will move, where will slip occur. Forces will be easier to move certain dislocations than others. Some dislocations will be mobile, others will be non-mobile, they'll be sessile. And we're going to get into all of this really, really fun topics in math in just a little bit here. And we're going to look at essentially the energy and how these defects form and how do they move and how they interact. And we're going to start off next time in thermally activated high temperatures with dislocation stress fields.